Welcome to this session. In today's video notes, we're going to be following up on our discussion of percent composition, and we're going to be talking about empirical formulas, which, when you're calculating empirical formulas, you're kind of doing the opposite of calculating percent composition. Instead of being given the formula and calculating percents, typically you're given percentages and asked to calculate the lowest whole number ratio of elements in a compound. So an empirical formula represents the lowest whole number ratio of elements in a compound. Again, empirical formula represents the lowest whole number ratio of elements in a compound. So let's look at an example. If we take glucose, which is molecular formula C6H12O6. That's its actual formula. We call that the molecular formula. That's what it actually looks like. It actually has 6 carbons, 12 hydrogens, and 6 oxygens. Again, that's the molecular formula. The empirical formula would be the lowest reduced ratio of that, which would be CH2O. So we could divide all those numbers by 6, and we could reduce it to the empirical formula. That's all the empirical formula is, just the reduced ratio. If we look at C2H10, we could reduce that to CH5, and that would be the empirical formula. C2H10 would be the molecular formula, and CH5 would be the empirical formula. Sometimes the molecular formula is already reduced and can't be reduced any further. So sometimes the molecular formula actually is the empirical formula. Some examples of that would be carbon dioxide, CO2, water, H2O, and methane, CH4. None of those can be reduced to a lower number ratio. But what we're going to focus on more in this session is not what empirical formula is, although that's important. It's how to calculate empirical formula. And there are really two different ways that problems will be presented to you when you're calculating empirical formula. The first one is calculating empirical formula directly from given masses of elements. So let's go directly into this problem, and I've already copied it out for you here. You don't need to recopy it. Just follow along with me. The empirical formula of a compound contains 0.0134 grams of iron, 0.00769 grams of sulfur, and 0.0115 grams of oxygen. So the first step in solving for whatever this empirical formula is to convert each of these grams to moles. So the first step is to go to moles. So the first thing I'm going to do is convert grams of iron to moles of iron by dividing by the molar mass of iron. And I get 2.40 times 10 to the negative 4th moles. Then when I take 0.00769 grams of sulfur and divide that by the molar mass of sulfur, which is 32.06, plug that into the calculator, I also get 2.40 times 10 to the negative 4th moles. And then for the last calculation, when I take 0.0 16.0115 grams of oxygen and divide that by the molar mass of oxygen, which is 16.00 grams of oxygen, I get 7.20 times 10 to the negative fourth moles. And I did round all of those numbers to 3 significant figures. So if you get slightly different numbers from me, that's how I got those numbers. And then the next step is to take a look at all of those moles that I've just converted to and divide by the smallest number to get the ratio of atoms. So if I look, the smallest number here is 2.40 times 10 to the negative fourth, and both iron and sulfur have that same number. So if I divide 2.40 times 10 to the negative fourth by 2.40 times 10 to the negative fourth, I'm just going to get 1. So both of those are going to be 1. But if I divide 7.20 times 10 to the negative fourth by 2.40 times 10 to the negative fourth, I get an answer that's pretty close to 3. And that means that my final answer is FeSO3. Okay, let's talk about the second type of calculation that you'll do for empirical formula, and that is when you are given percent composition instead of mass. So I've got a problem here for you that I've already copied out. And if we have 32.8% chromium and 67.2% chlorine, how can we calculate the empirical formula? So we've got this extra step that we're going to have to do, and it's a really easy step. All you have to do is assume a 100 gram sample. If you assume that you have a 100 gram sample, which isn't going to change your answer or anything, then 32.8% chromium becomes 32.8 grams of chromium. And 67.2% chlorine becomes 67.2 grams of chlorine. Then once you have everything in grams, all the other steps are exactly the same as the first problem that we did. Step 1, we have to go to moles. So we're going to convert 32.8 grams of chromium to moles of chromium by dividing by the molar mass of chromium, which is 52.00. And I get 0.631 moles. And then we're going to convert 67.2 grams of chlorine to moles of chlorine by dividing by the molar mass of chlorine, which is 35.45 grams. And I get rounded number 1.90 moles. And then I'm going to look at those two numbers and divide by the smallest number to get my ratio. So if I divide 0.631 by 0.631, I just get 1. And then 1.90 divided by 0.631 is pretty darn close to 3 on the dot. That's good enough to write just 3, so my final answer is CrCl3. That's my empirical formula. So here is one last final look at the first and second pages of the notes. We will be doing lots of practice with calculating empirical formulas. This is just one of those things that the more you practice them, the better you get. They also seem a lot harder at first than they really are. Once you get the hang of the steps, you'll come to appreciate how really easy these types of problems are.